Okay, so how is everyone today? Good, I hope?
Good.
All right. So last time we were talking about functions. We're still talking about functions.
Yay!
Yay.
I love functions.
So we talked about you can take two numbers and you can add them and get another number, and you can take two numbers and multiply them and get another number, and you can also divide and subtract them and get another number. You can do the same kind of thing with functions. And so in particular, we observe that if you take two functions, then each of them has a domain. You can make a new function by adding them together, and what will the new domain be? How do you find the new domain? Yeah, where the domains overlap, which is to say the intersection. The intersection, the domain of the new function is the intersection of the two that you started with. All right. So here we go. So this is basically the very last thing that we did last time. We talked about this thing called composition. So composition. So I could say let f and g be functions. So as for a mental model, again, I'd like for you to think about a function is like a machine, and you give it inputs and it produces outputs. So if we give the f machine input x, then the name that we give to its output is f of x. So that's what it does. And then if we give an input t to the G machine, then how are we going to name its output? G of t, right? And here's the thing about functions. They don't care where you get the input from. The only thing they really care about is whether or not the input is in the domain, right? You could have gotten it from Target or Walmart, doesn't matter. So thing goes in, right? Input goes into the function, and something comes out. And here's the new thing that we can do with functions that can't be done with numbers, is we can sort of wire them up so that the output of one function is the input to the next one. So specifically, we can do the following. It's called composition. So we can compose, which is to say, suppose that we give x as the input to the f machine, and then out comes f of x. Suppose we do that, and now suppose that we use this as the input to the G machine. Okay, so then what's going to be the name of the output? Right, G of f of x. And so now, if you take this, this multi-stage process, and you just sort of build an enclosure around it, just put a box around it, or a building, or whatever. We just do this. Then the name of the thing where you put in an x, and then out comes G of f of x. Right, and sort of ignoring what's in there. X goes in, G of f of x comes out. That thing has a name. Its name is G composed with f. So that's its name. So that's just like that open circle there is just like writing a plus, right? If you wanted to add two numbers, you'd write a plus b. And if we wanted to add these functions, we could write G plus f. But what we're doing is we're composing them, and the symbol for that is that thing right there, open circle. Okay. So this thing that we can do with functions, composition, is the reason why. It's the reason why functions are the central objects of study in math. It's also the reason why mathematics is used in all of the sciences. Okay, it's really not too much to say that this right here is the reason. The reason is that because you can consider processes, and you could take something like really complicated like making a car, you know, it's hard to imagine, you know, like digging dirt out of the ground, okay, and doing a bunch of stuff with it, and then eventually it's a car. You know, there's a lot of steps involved. But it starts by digging dirt out of the ground. So, you know, there's a guy in history, Henry Ford, who started Ford Motor Company. Now, he's a famous person, but he's not famous because he invented the car, because he didn't, right? Other people did. But he did do something like really innovative regarding cars. What was it that Ford did? Come on now. Everybody's got to know why Henry Ford is famous in American history. The assembly line, right? The assembly line. That's why. Because before that occurred, when you wanted to make something big and fancy, you know, like a car or whatever, you know, the way that actually worked is that you had one or two or just a small group of people who just worked on it from beginning to end. Okay, and these people had to be knowledgeable about every little bit, you know, regarding everything about making the car or whatever object it is that you're talking about. And so cars were only for rich people at that time. But, you know, then Henry Ford says, you know, well, what if I just put all these, like, stations in a row, and I only have to train these people to do, like, one little thing. You know, like, okay, now you know how to put the tire onto the rim. Okay, that's all that you do. And then goes to the next station. And then you know how to air up the tires. That's all that you do. And now suddenly, okay, you can start, you know, doing a lot of, making a lot of products, and it doesn't require, you know, experts, and it doesn't cost millions of dollars to make a single product. That's all that this is that X first goes to the F machine, right? We're going to do this first. And then when F is done with it, then it goes down the line, and now it's G's turn to do it. Okay, and there's nothing special about having two stations, right? You could have 22 stations. Right? They can be composed in that order. All right, good. So any question about this? So notably, what I want you to observe is that X visits F first, right? The input visits that one first, and then it goes down the line and visits G next. So here's an example. Suppose that we say let f of x be 2x squared minus 3x, and let g of x be 13x plus 14. Haha. So then, would you please compute this one, g composed with f evaluated at x, and then once you've done that, please compute f composed with g evaluated at x. So since this is the first time we're doing this, I'll get you started. So the first step here on this is you wanna write this thing without the composition operator, right? So specifically, notice that G composed with F is that. G composed with F is that. So this is G of F of X, like that. Good. Now we need to look at G's formula. So there's G's formula right there. So for any input, that's what G does with its input. That's what G does with its input. So what I'm going to do is I'm going to write down G's formula, but instead of writing an X, everywhere that I see an X, I'm going to put an empty parentheses, like this. So 13 multiply, and then, oh, I see an X, so I'm going to put a slot there. I'm going to put stuff in there in a minute, like that. Okay, so then whatever is being put into G, that's what needs to be put right there. Yes, you have a question? Well, so I'm working with G first. So what G does is it, you know, if that's an x, so it does 13x plus 14. And, you know, if that was a banana, it would be 13 banana plus 14. Okay, so then the question is that, you know, what are we putting into into G? You know, what is being put into G? You know, what will I see when I remove my red pin there? An f of x, right? So I put the f of x right here. So that's what G does. And now the question is that, oh well, what does f do then? So you know, now it's just sort of a copy paste, right? I just need to take all that and put it in there. So this will be 13 multiplied by all that. So 2 multiply x squared minus 3 multiply x, and then add 14. And now on such questions, it's always requested that you should multiply out and collect like terms and what have you. So this will be 26x squared subtract 39x, and then add 14. So any question about that one? So I'm going to move this prompt over to the left a little bit. Okay, so any questions about that one? All right. So how do we write this one without the composition operator?
Let's put G of x.
Right. So this would be f of g of x, like so. All right. So now, again, working from the outside in, let's look at f's formula. So that's f's formula right there. That thing right there. So what I'm going to do is I'm going to copy down f's formula, but everywhere I see an x, I'm going to write a big empty parentheses. So it'll be 2 multiply, and then I see an x there, so just an open parentheses there, and then subtract 3 multiply, and then I see an x, so open parentheses there. Okay, so then do you observe that you know, I've just copied down the structure of it, but I have made these slots that I'm going to write stuff into. Okay, so then well, when we're giving an x, that's what you do, but what are we actually giving to f? A g of x, right? So in all of those slots, in all of those open slots, now I'm going to write g of x. You know, and if we did f of rabbit, you know, then instead of writing those g's there, I'd have to draw a rabbit if I could do that. So then, now we just need to copy g's formula. So 13x plus 14, square that, subtract 3 multiply 13x plus 14. And then on all such questions, you know, the request is to multiply out and collect like terms. So this would be 2 multiply. Okay, so FOIL that out. That'd be 169x squared. And then plus, I have no idea, 13 times 14 times 2, because we get 2 of them. So that'd be 364. 364 x's, and then plus 196, and then subtract 39x, subtract 42. Now I'll distribute the 2 in. Oops. So that'd be 338 x squared 728 x's. $392 units, subtract 39 x's, subtract 42 units, almost there. So this would be 338x squared, 689 x's, $350 units. All right. Any question about that one? Any question about that? All right. So now we did. Well, let me ask. What's 13 plus 14? 27. How about 14 plus 13? 27, right? So, you know, it doesn't matter what order you add numbers in. So we had two functions. We composed them in this order, or we composed them in that order. Is the result the same? It's not the same. And I wanna emphasize to you that that should be entirely expected. Because, you know, again, this is like an assembly line. We have two things that we do. And you can either do them F first and then G, or you can take those and then put those machines in the other order, and you do G first and then F. And I want to emphasize to you that you should entirely expect that the results should be different. Because, you know, if we had a, you know, I think I've made this analogy before, right? If we had a doll making factory, you know, and there was a machine that put on left shoes, and another machine that put on right shoes, and another machine that put on left socks, and another machine that put on right socks. Does it matter what order the left shoe and the right shoe machine are in? Like when you're looking at the doll in the package, does it matter what order the left shoe machine and the right shoe machine are in? It doesn't matter. But what about the left sock and the left shoe machine? Does that matter? Yeah, right? It would. It would matter. Similarly, the pants and the underwear machine, right? One of them we'd be making a run of like Superman dolls. The other one would be like making a run of Ken dolls. You know, Barbie's companion. Right? It matters. Okay, good. So any question about that idea? Composing? So the reason why that's so fundamental is that when you want to understand a process, you know, which is like science, all of science and engineering, either understanding a process or designing a new process, you want to break it into individual steps. And from a math point of view, that means finding several functions and then saying that the overall function is the composition of these. So here we go. So this is a remark about identities. Identity. So first, we have the additive identity. All right, so the number, and then I need to fill in the blank there. So the additive identity is the number blank. It's the number that adding this number is the same as doing nothing. What number? 0, right? So the additive identity is the number 0. It satisfies the following, is that x plus 0 is x for all x. Okay. So now, you know, given two numbers, that's adding is one of the things that you can do to make a new number. You can add them. And then, you know, we're gonna single out as important 0 as the identity element because adding with 0 is the same as doing nothing. 3 plus 0 is 3. Similarly, the multiplicative identity is the number what number? 1, right? Because multiplying with this number should be the same as doing nothing at all. So the multiplicative identity is 1. That x multiply 1 is x for all x. Okay. So generally speaking, in math, anytime you have an operation like add and multiply, and there's lots of different operations that exist in the world of science and math and things like that. Every time you come up with one of those, you want to come up with you want to identify and understand what the identity element is, right? So then we already know what add is, and its identity is 0. We already know what multiply is, and its identity is 1. And now we just said this new thing. We said compose. Okay, so we need to figure out what its identity is. So the composition identity is so now the sentence structure has to change just slightly. So what's the next word I have to write? Function, right? Function. Because for these ones, we're talking about adding two numbers, right? We want to add two numbers, so the identity has to be a number, right? It has to be that kind of thing, the additive identity. And here we're talking about multiplying two numbers, so the multiplicative identity has to be the same kind of thing. It has to be a number. And here we're talking about the composition identity. So here the kind of thing that we're talking about must be a function. So is the function and then most of the time students don't know it before they get here. So the additive identity is 0, the multiplicative identity is 1, the compositional identity, its name is ID. That's its name. So now, because it's a function, I have to tell you how it's defined. I have to tell you what its formula is. That ID of x is x. That's pretty easy, right? That's a pretty easy function, right? So what I want you to observe is that it's basically saying that taking the mental model of functions as machines, if you take an x and you put it into the ID machine, then what comes out? ID of x. Right, ID of x, and I'll just write x because that's its formula, right? So x goes in, x goes out. So in that sense, in the sort of assembly line analogy, I'd like for you to understand that this is like a little bit of conveyor belt, right? It's just if you have products, materials going in on a conveyor belt into the machine, this is just like a conveyor belt. Okay, so observe. What if we do the following? What if we say f composed with ID evaluated with at x? So in the first place, how do we write that without the composition operator? That is to say, with more parentheses. Right. So remember, the rule is, one way to remember the rule is that x is closer to ID. So who sees x first? ID does. ID sees x first. So it'll be f of ID of x, like that. But what's the formula for ID of x? It's x, right? So that I can say that this is in fact equal to f of x. Right? So as a result, that's saying that that if you consider f composed with ID like that, well, that's the same as just f. So composing with ID on the right, that's the same as not doing it. What I want you to see is that's just like this statement. It's just like this one, right? So x plus 0 is x. X times 1 is X. F composed with identity is F. And so if this is the F machine right here, like this, you know, if that's it, I mean, sort of the assembly line analogy. What if I take this, you know, imagining this to be like a conveyor belt, you know, that bit right there at the beginning. Suppose I stretch it out really far, and I do this, say like X, and then really far, and then it finally makes it to the F machine, right? So I just made it really long there. So what would come out on the other side? F of X, right? It doesn't matter how long that is, right? It doesn't matter. That's what this is, right? X goes in, X comes out. That's just like a conveyor belt. That's what this is. Okay. Observe. What if we do it in the other order? What if we say, what is ID composed with F evaluated with X? So how do we write it without the composition? Right? ID of F of X. And so, you know, you gotta understand what the formula is. So there's the formula for ID. If you put an X in, an X comes out. If you put a 5 in, a 5 comes out. If you put a, you know, an avocado in, an avocado comes out. So what are we putting in here? An F of X. So what comes out? F of X comes out. Whatever that is. Right? If there was a conveyor belt, you know, and you could see it was just moving, you know, just down the thing, and if there was a giraffe sitting on it, you know, the giraffe would just keep going down the way. That's what this is. That's what all that this is saying. So as a result of that, this is saying that ID composed with F is what? It's just F. Right? So that's just like that's analogous to saying something like 0 plus X is X. 1 multiply X is X. But we have to do it in both orders. Why don't we have to do this one in both orders? Right, because addition commutes. Because 0 plus X is the same as X plus 0. And multiplication commutes, so that's fine. But does composition commute? It doesn't, right? So you have to check both orders. Again, so if I take the F machine and give it an X, then out comes F of X. But what if I do this? What if I say, okay, I'm going to give an X to the F machine, but then I'm going to make the conveyor belt that comes after it like really long? Then what would come out right here? F of X, right? Okay. So now to sort of prime you for what's going to happen on Wednesday, we're not going to get into this exactly right now, but to prime you for what we're going to get into on Wednesday, I'll say the following: is that we're going to want to compute inverses of things. So now we've got 3 operations. We've got add, multiply, and compose. So for every one of those operations, there is a notion of inverse. So for example, what is the additive inverse of 5? Negative 5. Now, why is negative 5 the additive inverse of 5? Because when you add those things, you get 0. And what's special about 0? It's the additive identity. So now let me stress the words here. What is the additive inverse of 5? It is negative 5. Because when you add 5 and negative 5, you get the additive identity. Right? 0. Similarly, what is the multiplicative inverse of 2/3? 3/2. How do you know it's 3/2? Right, because when you multiply 2/3 and 3/2, you get 1. And the reason why that's significant is that 1 is the multiplicative identity. Right? So then on Wednesday, we're going to look at functions. And we're going to want to compute the compositional inverse. We're going to want to compute compositional inverse. And how will we know when we have found the compositional inverse? Yeah, when you compose them, you get the compositional identity. You know that two things are additively inverse when you add them and you get the additive identity. You know that two things are multiplicatively inverse when you multiply them and get the multiplicative identity. You know that two functions are compositionally inverse when you compose them and you get the compositional identity. So do you get the structure? You know, if there was some other operation called banana, then you'd be able to say that these two things are banana inverses because when we banana them, we get the banana identity. Okay? Good. So we'll talk about that on Wednesday. But any question about this? All right. So now for the rest of the day and part of Wednesday, it's going to be opposite day. We're in section 3.5. And this is called transformations. All right. So now we're going to go with the following fiction. Okay, so then, so I need you to imagine that you can't see my my hands there, and you can't see, you know, anything except this sheet of paper and this this pen, and all the background stuff. It's not there. So watch. I'm going to move this pen to the right. Are you ready? See me move that pen to the right? Do it again. Do it again. Okay. I'm going to move the red pen up. Are you ready? And you know, to that you might say, no. I can see that the thing. Then you're not pretending right? I said that you can't see any of that stuff there. You can just see the sheet and the red pen. That's all you can see. Okay. So then now I'm going to move the red pen to the left. See me doing it? Okay, so now that's a little bit weird, but here's the deal: is that the reason why I took the time to do that little silly thing is that we're going to be taking plots of functions, and we want them to move. We want them to have a certain motion. But what's going to happen is that we're not actually going to move the plots of functions. Rather, what we're going to do is we're going to move the coordinate system underneath them. So it would be like if you hung a picture for someone and they said, you know what, that looks pretty good, but you know, I'd like for you to move it like 6 inches over. And so you say, all right, and then you hold the picture still and move the whole house 6 inches the other way, right? Okay. Alternatively, here's another point of view: is that we're going to want to make stuff bigger and smaller. But we're not going to make the object itself bigger or smaller. Rather, we're going to do the opposite thing to the world. So here's a typical example. So I've got a daughter, and she's little, like even little among her colleagues, right? She's just going to be not big, and that's, you know, I refer to her as the biggest little girl, but that doesn't really do a lot. So when we go to like theme parks, and it says you have to be this tall to ride, you know, it ain't happening. You know, so then if I was magic, you know, I could like just stretch her out, you know, just. But you know, if I was magic, I'd still be a parent, so probably I would say it's not her problem, it's the world, right? This world is messed up. So then instead of, you know, modifying her, I could just shrink the whole park, right? If I just shrink the park, and then all those signs will shrink also, and then you have to be this tall to ride, and this should be fine. You get it? The idea? All right. So here we go. This is a horizontal shift. So we could say let y is f of x be given. So if we were to look at a at the plot of y is f of x, suppose that the plot looks like this. Suppose that the plot looks like that. So, you know, that's like the plot of some kind of parabola or whatever. And then, so, you know, that's the plot of y is f of x. And suppose that we take that red plot there. We take that red plot and this is where it previously was, that green point anyway. That green point was previously right there. But now, in fact, what's going to happen is I'm going to have taken the red thing and just moved it over a bit. So I take it and move it over. To like right here. So that point, you know, went over there. And now it looks like this. So can you see what it was that I did? It is like I took this and moved it over. Okay, and let's furthermore, let's say that the distance I moved it over was c. So, you know, on some scale, you know, maybe that's like I moved it, you know, 6 inches to the right. You know, you hung a picture and someone said, move it over. So I moved it, that distance there is c. Okay, but now I'm going to tell you that that's not actually how I did it. What I actually did is that, you know, the request was made. So what I did is you know, I put my thumb on that red bit there so it wouldn't move. And then I grabbed the coordinate system, and what did I do with it? Instead of moving the object to the right, I pulled the coordinate system to the left, right? And I pulled it that way. And then you take a look, and then there it is. So do you get the idea? So because this is a horizontal transformation, what variable must have we been playing with? The x, right? We must have been playing with a horizontal coordinate. And did it go up and down at all? No, so we must not have been playing with the y coordinate. So the equation is going to look like this. Y is f of, but now we played with the horizontal coordinate. So now we've got to say what we did. So the object, you could say the object moved c to the right. Alternatively, you could say that the coordinate system moved c to the left, right? Correct? So then the way you write it is like this. X and then minus c. So to get something to move to the right, you actually move the coordinate system to the left. All right. So, for example, I could say something like, well, please sketch from memory now. Please sketch y is the square root of x. So that's something that you should just know. So how does it look? Right? So it starts there at the origin and then it goes like that. Okay. Fine. Then in that case, would you please sketch y is the square root of x minus 3. So in the first place, Tell me, what are you expecting to see from that one to that one? A shift, right? And what's moving, and how does it move? So suppose we say that the plot is moving. Then how does the plot move? 3 to the right. Okay, suppose that we say that the coordinate system is moving. How does the coordinate system moving? 3 to the left. It's not that both of those things are occurring, like first this, then the other. You have to say it this way or say it that way. Okay, so that means that, you just move over like this. Oops. So that would be there at 3. All right. What about this one? Sketch this one. Y is equal to the square root of x plus 2. So now what's happening? Okay, the plot is, right? So the plot is going to move left. The axes, the coordinate system, the thing, is going to move to the right. Interesting. Any question about this? Okay. Now, if we can do it with x's, if we can do it horizontally, then we can do it, vertically. We can do it with y's. Okay. So let's do it with y's. So let y is f of x be given. So suppose that this is the sketch. So, just, something. That's the sketch of y is f of x. And then now, instead of making a horizontal motion, let's make a vertical motion. So notably, I'll say that that point, originally was right there. So it was originally right there. And suppose that we move it up to, right there, say. And that distance is again c. So you hung the abstract art on the wall, and someone said, "Hey, could you move it up c inches or whatever?" So one way to achieve that is to take the nail out and then move it up or whatever, or you could just hold that all still and then just tear the house down and build it all back up 6 inches lower. That would work too. So because this was a vertical movement, then what variable must we have been playing with? We must have been playing with y. And was there any horizontal motion? There was not. So as a result, that means that the right-hand side is unchanged, right? You can write this, something blah blah equal f of x. But what will we need to write for the left-hand side? Y minus c. And the interpretation of the minus c is that you can achieve this effect. You can achieve this effect by someone says, "Hey, can you move it up c inches?" You can hold that red still, and then instead of moving the red up, you can grab a hold of the axes and pull the axes down. And then you have that. Now, that's not what the book says. So the book says it like this. it says that, you can put the C on the other side. No dispute. Of course you can. But you need to pay close attention to the following, and that is the following remark. Is that a horizontal shift looks like this. So y is f of x goes to y is f of x minus c. A vertical one is like this. So y is f of x goes to y minus c is f of x, like this. So this is the way that I write it. The reason why I write it that way is so that it's always minus c. And if it's horizontal, it's always with x. If it's vertical, it's always with y. And the book is writing the c on the other side. There's nothing wrong with that, but here's the deal. Can you get this c in the horizontal case? Can you get it to go to the other side? No, because it's it's locked in the jail there inside of the argument. It can't come out to play. Whereas this one can move side to side. So you can write it either way, but I just want to make sure that you understand the consistency. Because the first thing that we do on Wednesday is to talk exactly about this, but instead we're going to be scaling, making things taller and shorter. All right, have a nice Monday.